Right, so welcome everyone. It's a great pleasure to have you here. I'm John Antoniades. I'll be trying to give you an introduction of Argos for the next hour or so. But before we do that, I just want to, welcome. Say a few things about the logistics and the structure of the meeting. So first of all, a few things about the host. So we are, for those who participate in person at least, we are here. That's great. So in between all the mountains, the goats, the olive trees, there is this institute, so the fourth Foundation for Research and Technology, ELATS. This is the host of this meeting. So I'll say a few things about Fourth. So Fourth was founded about 40 years ago, and it's the largest research institute in Greece at the moment. It consists of 10 institutes covering anything from biology, electronics, mathematics, astrophysics, computing, and everything in between. There are about 1,600 people and about 150 research groups. So one of these institutes, I think is the latest addition to this Fourth, is the Institute of Astrophysics that was founded in 2018. Still a very small institute. It's actually located in the physics campus, not in this building. So up to now, we're just 5 faculty plus another 5 or 6 affiliated faculty from the University of Crete. There are also some research fellows like who come here often and do part of the research here, and about 55 members. And very and most of this research is actually funded by the European Union through ERC research grants, EC grants, and so on and so forth. So that's both good and bad because funding goes, who knows what happens, but very proud of that. So a few of the things that we do. So the research covers anything from cosmology to time domain. So a few of the projects you can see here. So the Institute of Astrophysics operates the Argos Observatory, which now hosts 2 optical telescopes. You can actually see the observatory through that window here, and we will visit tomorrow for those who participate in person. There are instruments that do polarimetry, very good instruments like RoboPort. There's an ERC project called Pacify, which is about building a wide field polarimeter that will be mounted on the 1.3 meter telescope at Skimatas. There's also Turbo, which will be, I like to call it the optical counterpart of Argos. So it will be an array of 16 small optical telescopes that will be doing optical follow-up of gravitational wave transients and supernova surveys. So that is going to be operational in about a year from now. We do a lot of research on VAI, so Carolina's group. We do cluster timing arrays, Argos, of course, and lots of other stuff as well. Regular partners in crime, it's the Institute of Computer Science, who also were trying to convert to astrophysicists. So very recently, for instance, there was an ERA chair grant awarded to the signal processing lab of the Computer Institute, and the lead of this project is Jean-Luc Stark from CA, who is going, for the next 5 years, it is going to build a new astroinformatics group here at Fourth. So the goals of this project is to establish this astroinformatics program at Fourth. And the goal of this group will be to build things like resource efficient deep learning for inverse problems, high dimensional problems, time domain. So some information about the logistics coach. Crash is too often. So the agenda has been posted online. There might be some last minute changes, so make sure to check it regularly. Please join the Slack channel for offline discussion, questions, and everything else. All or most sessions will be recorded. So if you don't want to your presentation to be recorded, or you don't want the discussion which you take part in to be recorded, please, there's a Google form that circulated yesterday, so please fill your preferences in that form. So we'll take a few pictures. We have to take a few pictures. So the first one for the in-person participants will be tomorrow before lunch. And we'll try also to do an online screenshots on Friday, also before lunch. And then we'll try to take a few pictures of the conference. There's an excursion tomorrow, if the weather permits, which looks promising for now. We'll visit the Skinakas Observatory. So that's about an hour drive from here. And then we'll also visit the Nida Plateau, which is one of the candidate sites for the deployment of Argos. And from there, it's like a 30, there's a nice trail. It's about 30 minutes to get a walk, hiking, to get to this nice cave, which is supposed to be the birthplace of Jerusalem. So we can do that tomorrow for those interested. And the dinner, oops, I forgot to do this. But anyway, so the dinner will be at Pesquesi, so I will give you more information probably later today about that. So that will also happen. Am I forgetting something? Any questions for so far? Right, so for the in-person participants, please make sure to, so we need your signatures for reporting reasons, so please make sure to sign the forms that are right, so I will now say a few things about Argos and about the meeting. So what's the motivation for Argos? Obviously, for those of you who are astronomers, I don't have to explain too much, but for the rest of you, there's this big revolution happening in the past decade. Astronomy, thanks to a new way that we have to observe the universe. That is, for the past decade or so, we have instruments that can observe the entire sky at all times, at multiple wavelengths. And this new mode of observing has resulted in many scientific breakthroughs. So this is a very famous image that was by Fermi satellite. So Fermi is an instrument that observes the sky in gamma rays, and it has been observing the sky for the past decade. And through these instruments, we have remarkable insights about high-energy phenomena such as gamma ray bursts, supernovae, pulsars, and so on. And this is now
Όχι πριόνι μεγάλο. Ωραίο. Άρα εγώ αυτό που θέλω τώρα είναι ότι... Άμα θες απριόνι και αυτά... Όχι παιδί μου, δεν θέλω κάτι.
Okay. Right. So And that is true for, there are now multiple satellites, multiple instruments that do that in many wavelengths. So this is zero zeta and the X-ray. So that's more insights into, again, high energy phenomena and extreme accretion and so on and so forth. There's obviously many instruments that do that also in the Gaia. And so one wavelength that is missing from this particle is obviously radio astronomy. So if you want to build an instrument that observes the survey instrument radio wavelengths, so there are a few ways to go about it. So first of all, obviously you need something that has a large field of view, combines large field of view with a large sensitivity and good resolution. And traditional radio telescopes, it is very hard to achieve this with the traditional radio telescopes. So single dish telescopes. And that's because you basically cannot make an instrument that has all this meets all these requirements at the same time. So this is where radio interferometry comes to the rescue. So if you use radio interferometry, then you can coherently combine signals from many telescopes, and then you can build an instrument that has the a sensitivity that is proportional to the total collecting area of your dishes. The resolution that is defined by the maximum baseline, and the field of view that is defined by the diameter of the dishes. So if you want to make an image using a radio interferometer, there are a couple of ways you can go about it. First, you can, if you have just a few antennas, then you can basically have to wait for the Earth to rotate to fill the big day. Another way to go about it is if you increase the number of antennas in your array, then you can more easily fill the UV plane and make a good image without having to wait for the Earth. So this is the so this is what Argos and other what we call big and small D interferometry trying to achieve. Of course, there are some challenges to overcome if you want to do this. So one of them has to do with computing power that you need to correlate all these instruments, and that computing power scales with the square condition. So up until recently, that basically could not be achieved with available technology, but this is no longer the case. So this is something that is currently possible with existing technology. So we do have a few examples of such instruments already, some of which you can see here. So there is Astra here in Australia. This is a very old example. This is Jacqueline Bell. Of course, she also used the North instrument to discover pulsars, although she didn't have digital receivers. She used analog receiver at the very narrow receivers. There's Chime, there is obviously all the SK pathfinders, and all these instruments have been operational now for a few years, and they demonstrate they have all led to significant breakthrough discoveries from time domains, so bits to cosmology. So it's clearly all this is a huge discovery. This type of so in a nutshell, this is what Argos is about. Is about designing and creating big big and small d interferometry. If we don't sensitivity L-band to SK1 bit. And there's a reason for that, because we want to follow up on SK discoveries. And in order to do that, we to build up to this collecting area, we need about 1,000 6-meter dishes. So that gives a field of view of about actually 15 square degrees. It's the time field of view, and the only way you can build such an instrument is if you use ambient temperature amplifiers, ambient temperature techniques, and that's also it's now becoming possible in past years. So in terms of baseline and resolution, the target resolution, at least for imaging, is of order an arcsecond. We want to do tracking in both directions, and that would be a single band instrument that would build broadband receivers that cover 1 to 3 GHz. And there you can see some of the specs. So why this design? So there are a few reasons and constraints that are not directly related to science, but are more related to the funding call through which the Argos design stack is funded. So one of them is low cost. So if you just take an instrument that has 1,000 dishes, 1,000 6-meter dishes, and divide the total cost by the number of antennas. So first of all, the total cost, because the dishes are small and all the main hardware components for the correlators you can buy off the shelf, the cost is very small. This is just a very small fraction of the SK cost. And then it's also sort of scalable. So if you just divide the total cost by the number of antennas, that comes to about 40 to 50 K. So you basically, that's a reasonable amount for any partner who wants to invest in this to be able to do it. So the entry barrier is very small. It's also expandable and modular, so you don't really have to build the entire thing at one go. You can just keep adding sensitivity antennas to the instrument as you go. And we also wanted to be complementary to other facilities. That's both in terms of wavelength coverage, so we want to tap into the SK discoveries, for instance. We wanted to be complementary in terms of location, so both in longitude and latitude, to other facilities such as the DSA, for instance, and the SKA. And because of the large reliance of off-the-shelf components, we also want to build incentives for private sector involvement, both in the construction of the instrument and later in terms of providing some possible services to companies. And also we have to respect some local environmental constraints. And I will probably, we can discuss this more in the course of the meeting, but that also translates to something that is a small total footprint and a small footprint per element. So if you wonder why the 6-meter is, so that also somewhat related to cost. So if you just fix the sensitivity, so if you say I want to build an instrument that has X sensitivity, then this 6-meter diameter per element is sort of the sweet spot, because if you make your this smaller, then the cost for the correlation increases exponentially, and then if you make your dishes larger, the cost also increases. So that's sort of the sweet spot that also gives you a very good field of view, a very good service. So just give you an overview of the science that we want to do. There will be many talks about that during the meeting. So one of the things we want to do is not related to the large field of view of the instrument. It's related to the sensitivity, and that is continuous monitoring of millisecond pulses. So we want to spend a significant fraction of the operations timing and observing millisecond pulses, and more specifically millisecond pulses used in pulse dynamics. So for the non-astronomers, millisecond pulses are basically, you can think of them as very stable clocks, very stable locators. So there's one technique that uses these pulses to monitor, uses these pulses as a gravitational wave galactic scale gravitational wave interferometry, interferometer to search for low frequency gravitational waves. And very recently, this technique has yielded very exciting results. So there seems to be a very strong evidence for low frequency gravitational wave pattern using this technique. So with Argos, with an instrument such as Argos, we will be able to do daily timing of most of these PT pulses. And also that will be useful for a few things. So first of all, it will be useful for noise modeling purposes, because a lot of these pulses are, these pulses are physical sources, so we have to be able to characterize them better, and the only way to do this is by observing them more. So it's kind of, we now know that this is required. And the other reason is that by increasing the cadence, we also increase the frequency span of this the sensitivity at higher frequencies of this pulse. And that's because the high end of the sensitivity curve is basically defined by the cadence. So by doing these daily cadence observations, we sort of will be able to bridge the gap between leads and cadence. And so there will be a couple of talks later today in the timing session about that. Again, related, so pulsars are also interesting sources by themselves. And so we want to observe additional pulsars to be able to measure the masses, for all sorts of other reasons. And so we do expect that a lot of the time the instrument will also go to observing other pulsars. So there will be talks about that later as well. Another thing is what we call image plane transients, and that includes anything from daily monitoring of point sources, basically of all the point sources in the field of view of the instrument, follow-up of gravitational wave events as well, and follow-up of other triggers such as gamma ray burst triggers, and so on and so forth. And so there will also be talks about that after lunch, I believe. Obviously, having an instrument with a large field of view and good sensitivity, we also want to do time domain stuff. And one obvious thing is fast radio bursts. But we aim for, what we designed the instrument to be capable of, is to do a commensal FRB survey in its entire field of view, and we do expect to find with full-scale instruments several tens to hundreds of well-analyzed FRBs per week. And because it's of the relatively, because of the S-band frequency coverage, we will also be able to find FRBs that are relatively highly scattered and in denser environments. So there will be talks about that by So say a few things about the Argos conceptual design study, which is the project that is was recently funded by the EC and is started in January. So the design study for the instrument is basically the consortium consists of five partners. So one is the Institute of Astrophysics, the Institute of Computer Science, also at Worth. There's the Max Planck Institute for Radio Astronomy, the CEA in Paris, and the University of Piraeus Research Center in Athens. And that study is now funded by Horizon Europe Infrastructure Development Fund. So what we want to do with in this project is basically we use like an integrated approach of both science, engineering, and also looking into new technologies to make a fully costed detailed design of the system. So that's sort of the timeline of the project. So we're currently in the early phase of the design, which is the requirement analysis, high-level design. And the first milestone of the project was actually this workshop, where we want to get community input for the high-level requirements in the design. The next phase is again the high level and component level design that will lead to the preliminary design review that will happen in June next year. And after that, we'll enter the detailed design and prototyping and validation phase, where we'll do the detailed subsystem design, and we will also build a prototype as a 6 to 10 days prototype that will based out here at the campus. And the 3-year project will conclude with the technical design review and the design. The final delivery will be the design. So this is sort of the structure of the consortium. So we have 9 work packages, including project management. There's a science working group, so there's basically one work package related to science, and most of the effort goes to engineering, of course. There's different sub packages for site characterization, site selection, the front-end development, the back-end development, and the database and transit detection algorithms, all the science pipeline as well. A few of the things that we do. So we do a lot of technology pathfinding. For instance, as I said, we were trying to adapt off-the-shelf solutions to make them to build something that is low cost. That's also related both to the front end and the back end, so there will be talks about that later today. There's a lot of development effort that goes into designing the front end. That is led by the University of Piraeus and the Max Planck Institute for Radio Astronomy. So there will be a talk by Leonidas later today about that. There's a finding related to the digitization. So the digital part of the signal chain. So basically, what we want to do is to use these RF boards to do the digitization at the front end, and then that is an effort that is led by Yuan Bar's group at the Max Planck. So there will be the second talk of the day. There's also some effort related to building this efficiently, doing efficient high performance computing for the correlator. So we're using this microservice approach to build a correlator. That is also something that we put a lot of effort in. So site selection, we also do site characterization, so RFI characterization, weather characterization, and some candidate sites here in Crete. But this effort will also expand to main location in Europe. So this place we're going to visit tomorrow is the Nida Plateau, and you will see some results about that. Um, I believe tomorrow. Right. So as I said, we did the first RFI measurement campaign in June. So we used this sort of tracks there. We partnered with RFI measuring equipment and took them to the mountain, and we have some very interesting, very promising results from that campaign. So Thanasis is going to talk about that as well. So again, another work package has to do with handling and analyzing all the science products that will be coming out of the instrument. And that obviously is a big data problem that requires new approaches, artificial intelligence approaches, and state-of-the-art statistics as well. And that is a group led by CA, and Sam will talk about that. As I said, at the end of the project, we will also have a pathfinder, a 6-stage prototype. So we are now in the process of thinking what we can do with the instrument. And some of the things that are relevant for the full-scale instrument are also relevant for the pathfinder. We want to do high cadence pulse timing, FRB detection and monitoring, manual tasks, and then also some image based stuff as well. So that brings me to the end of my presentation, and I just want to say a few things about what we want to achieve in the workshop. So there are some critical questions that we want to get input for. So one of them is obvious. What are the key specs and capabilities in terms of sensitivity, contrast, resolution, and so on and so forth, that will allow all this breakthrough science in all these different domains, right? Oops. So, yeah. So relevant near future technologies, for instance, obviously there's this question of this ambient LNAs, this very obvious, this RF SOC boards, and also there's this RISC-V based CPUs and accelerators that may be relevant to the project. So there will be talks about that as well later in the week. So what is the preferred access model for the instrument? Initially, what we aim for, what we design, is an instrument that will be delivering science-ready data to the public, but there's also the question of if there could be some hybrid or some other access model that would also give more incentives to people to join the collaboration. There's the question of VLBI and log baseline stations. So can we install part of the instrument in a different in a long baseline station? So question is, can we build something that you like LOFAR, for instance, that will significantly increase the resolution of the instrument? So do we have the necessary technology to achieve that? And then there's also the question of funding, synergies with other projects, other infrastructures, SKA, obviously, and what are the opportunities for both informal and formal collaboration between these projects. I don't know why that, yeah. Anyways, and just to keep things and also what would be the concept of operation? So how much time do we spend doing each of the stuff. So how much time is required to do for timing, for imaging, can we do some of these things, so on and so forth. So these are just some of the questions. Obviously, I'm sure you have more, and I'm looking forward to discussing more of this days. So I'll stop here and yeah, take some questions. Questions?
So I didn't want to ask this because I think it might come clear later on, but what after the conceptual design, yes, what is your model for funding the whole thing, the whole structure? So are you looking for external partners? Are you what's your model for moving forward, basically?
So both, I would say, both external partners and so basically, what we're currently, most of the effort right now goes into finding regional funding. But also what we want is to find a model that will allow people to just invest in this using because as I said, we basically want to keep the entry barrier small. So we want to bring in university partners, institutes, and so on. So now we can start the conference.